Hi students, Professor Nugent here. Let's talk about the consequences of misspecification of the variance function when carrying out weighted least squares estimation. When we say misspecification of the variance function, we mean that the conditional variance of u given x is not equal to sigma squared times h of x for our chosen function h of x. The two primary consequences are that the WLS standard error and test statistics are invalid. The other main consequence is that we will not be able to rank weighted least squares and OLS in terms of efficiency. It's important to keep in mind that misspecification in the variance function does not cause bias or inconsistency. I want to comment first on the last one, and then let's talk about the two consequences in detail. This last note that misspecification of the variance function does not cause bias or inconsistency is the result of 1, the multiple linear regression assumption number 4 being satisfied, so that the expected value of u given x is equal to 0, so that any function of x is still uncorrelated with u. This implies, 2, that the weighted error is u over square root of h of x is uncorrelated with the weighted regressors, and our weighted regressors are the xj over square root of h of x. So as our weighted error is still uncorrelated with the weighted regressors, a result of any function of x still being uncorrelated with u, this gives us the result that misspecification in x will not cause bias or inconsistency. That is misspecification in h of x. That's important. Misspecification h in x will not cause bias or inconsistency. Cool. So we still have unbiased and consistent estimates using weighted least squares. Even if we misspecify, we get that variance function wrong. Now let's take a look at the consequences. Number 1, as we discussed, the weighted least squares standard error and the test statistics, the coinciding test statistics, these things are going to be invalid. There is a pretty easy fix to this. The fix is to obtain standard errors for WLS that allow the variance function to be arbitrarily misspecified. So let's take an example and see what we mean. Suppose that we start with a model yi is equal to beta naught plus beta 1 x1I through beta k xki plus ui. So we have an equation yi equals beta naught plus beta 1 x1I through beta k xki plus ui, and we have heteroscedasticity in the error term. So we want to transform this regression using weights. We want to weight the observations that have larger variance with less weight. The weights that we use are 1 over hi, and these are the weights that are given to each squared residual. So this means that we're going to use a multiplying factor of, so we multiply through by 1 over square root of hi to transform the equation. So if yi over square root of hi is equal to beta naught over square root of hi plus beta 1 times x1 I over square root of hi through beta k xki over square root of hi plus ui over square root of hi. Now, if we have the correct functional form for the conditional variance, then this term demonstrates heteroscedasticity and this term demonstrates homoscedasticity. But what if we're saying, what if the variance of ui given xi is not equal to sigma squared hi? So what if we have weighted by the wrong function? Then this term does not demonstrate homoscedasticity, so we have not fixed the heteroscedasticity problem. So we still have heteroscedasticity in our equation. So what can we do? Our fix is quite simple. We can use the heteroscedasticity robust standard errors. So it's good practice to use heteroscedasticity robust standard errors even with weighted least squares estimation, because it's hard to know whether one has truly modeled the functional form of the variance correctly. If one has not truly modeled the functional form of the variance correctly, then this term the ui over square root of hi will still demonstrate heteroscedasticity, and then our standard errors and test statistics will be invalid. So we may be improving the efficiency of the estimates a little bit by using WLS. It's possible. Again, it's hard to rank OLS and WLS if we get the functional form wrong. And it's hard to know, so we should also use heteroscedasticity robust standard errors to buy down that risk. So that second point, let's get to that and just talk about that for a second. If we have misspecified the variance function, so if this is happening, right? So the conditional variance of u given x is not equal to sigma squared hi for our given function, our chosen function h of x, then as we have just discussed, we cannot rank OLS and WLS in terms of variances or asymptotic variances. So it's hard to know which estimator is more efficient. But in cases of strong heteroscedasticity, it's still important to model that heteroscedasticity, even if correctly, and apply WLS rather than ignore it altogether. So you can give it your best try to model the heteroscedasticity, and then just use heteroscedasticity robust standard errors to buy down the risk. That's it for consequences of misspecification in the variance function. Stay tuned to the next video for prediction and prediction intervals with heteroscedasticity.